Okay, we have one last, I would say, comment on linear systems to touch upon, and that is on what's called a condition of the matrix or the system that refers to how well posed the system is. Not all linear systems are made equal, and some of them really misbehave computationally and cause a lot of errors. And what we typically refer to stability in numerical methods is that if I have a linear system, all of the coefficients within, both in matrix A and the right-hand side B, which is typically boundary conditions. So typically your matrix A will describe some sort of physical constraints of the system. If you remember when we were forming the linear system of going through the pipes, then those coefficients in matrix A are technically related to how much flux can go through each of the pipes and how well connected they are. Okay? So that's something that is related to the physical description of the system. And then those boundary conditions on the right-hand side, they're typically related to what is your influx into the system overall and out of it. Okay? If you remember the system where we had the model of the heated rod, again, the middle of the system is basically related to that heat transfer coefficient H out of all of the nodes towards the air, whereas the boundary conditions, the temperature on one end and the other end was playing into the right-hand side. So sort of like boundary conditions are typically, or things that we know, are typically on the right-hand side after you build your linear system. And the coefficients of the matrix A are typically some sort of physical parameters that are limiting whatever flow you have or whatever transport you have within the system. So our questions from the terms of stability or how well posed things are typically related to, okay, if I change, let's say that I'm an engineer building some network of pipes that flow through, right? If I change those pipes slightly, or if I vary them in some way, that they're not that far away from what I just had, then I would expect the solution to this problem not to change much either. And it turns out that sometimes, so basically those conditions that I set up have a major influence on my solution. And if I change my conditions very slightly and the solution just goes berserk, which it can, then my system is not well posed. It's not a stable numerical system. Okay? And it can numerically, it's kind of unrelated to reality, right? That is guiding it. And that can be a problem. So we don't like such problems. And there's a whole lot, however, sometimes we can't escape them. And there's a whole lot of numerical work by applied mathematicians making systems more stable or converting them to a better behaved system numerically that will converge faster and get us more accurate solutions. So in order to actually measure these things, we actually need to introduce matrix norms. So we've had norms of the vectors before. So normally when I'm looking at just numbers, we refer to the absolute value to see the relative magnitude of things and compare them. When I'm in the vector world, I have to use the norm. And then we introduced three norms. There was one norm, two norm, infinity norm. Okay? We could have infinitely many more p norms introduced. But overall, we pick one or the other. They have slightly different flavor and are picking slightly different things out of this matrix. Okay, so for instance, infinity norm will focus on the worst case, the largest thing in your entire vector. The square norm will square everything, then sum it up. That means that relatively speaking, larger numbers will dominate with that square. And the smaller numbers will get relatively smaller, so it will get diminished. And then you take one square root of all of that sum. So basically, 2 norm is technically related to, like it's going to be slightly in favor of larger numbers. Though it's also related to our Euclidean distance, so we are used to measuring things in that way. It's basically the shortest distance between two objects in space. And then I have one norm. We know often it's kind of a little constraint. It's taking everyone equally, okay, absolute value of each number, and then just sum them up. And we also know that it's kind of a constrained distance. If I'm on a grid, okay, I cannot fly. I'm trying to, but I cannot. Okay? So I have to actually go along the streets. And one norm will actually give me some of this plus some of this. That's the distance of getting from me to her on a grid. So all of the norms have slightly different flavors. However, altogether, when I'm looking at the stability of the numerical iteration, whichever one I pick to actually measure if I'm getting closer to the result is fine. They're all actually ultimately related in one way or the other. So now we will actually introduce some norm for matrices. Though I'm having now trouble with this large system because it's now a table of numbers, and I could just extrapolate the numbers from vector norms to matrix norms, but that's not necessarily physical, or it's not related to what are we trying to do with those matrices. So technically there's this Frobenius norm that I could use that simply goes and squares all of the numbers in the matrix, adds them up, and takes the square root out of it. And it looks like it's directly related to L2 norm, but it's a bit of a dumb extrapolation of that norm. A smarter one is actually looking at so this is a Frobenius norm. It's easy to compute, that's great. That's what's great about it. But better norms are those that actually take A as an operator. And that operator is mapping vectors to some other vectors. Okay? That's what, it's a linear transformation of a vector. When I do AX is a vector, AX is another vector. And depending on the dimensions of that matrix, I could even go from different spaces. It could be Rn to Rm, right? So I can actually go from two-dimensional space to three-dimensional space and so forth, depending on what my application is. If I stay in one place, one common thing that we can denote with matrices is rotation. Okay? Rotation has a matrix description, and it will rotate vector from here to here. Things like those. Translation is simply addition, right? And so forth. Okay, so great. So how do I actually relate that? Technically speaking, what we want to look at the norm is we want to relate the norm if I restrict myself to vectors that are size 1 in whatever norm I want to, let's say 2 norm. So those are vectors on a sphere. Let me see, when I look at the mapping of those vectors using AX for all those vectors from the sphere, where are they going? Okay. And let's see the norm of that. Okay. So technically, what we are looking at as a norm of a matrix, which is really linear operator A, is the maximum of where all of those vectors went. Okay. It's a little harder to compute, but physically it makes more sense. So let's say that I have a matrix A that is just 2's on diagonal, right? That's just going to stretch any vector twice. Okay. So basically all of my vectors of size 1 will go to vectors of size 2, right? So the norm of my operator A is 2, because it's stretching things by 2. Okay? So that's sort of the physical meaning of this. But the formula looks a little ugly, and it's not necessarily easy to compute. I could actually go and draw things and take a sampling of these vectors on the sphere and just see where they go. So I could numerically come up with an algorithm that does this, right? And there are algorithms that do this. Luckily for 1 and infinity norm, all I really need to go and do is do a maximum sort of 1 norms of, in this case, columns and in this case, rows. So I take, in this case, sum of absolute values for j's as j go all of the, through all of the columns, right? J. So let's say norm 1A of this first matrix A. What would it be? Whoops. I think we're going to hit the same problem again. Just a moment. So if you have a matrix A, 1, 2, 3, 4, 5, 6, 7, 9, 8, write down a norm 1 of it, please. And I'll be right back with you as I... So go down each, take for J, any J, right? J's are my columns, so take row, entire row I, and look at the absolute values of those numbers and sub them up. So that's basically L1 norm of that row. So find a norm of every row, and then find the maximum of those three numbers. And it's a simple matrix 1, 2, 3, 4, 5, 6, 7, 9, 8. And meanwhile, I'm gonna fix my wireless connection if I can. 2, 1, 2. Okay. Just get stuck. Let's try HDMI today. All right, HDMI decided to work today. Awesome, continuing. So I just said 4, 5, 6, 7, 9, 8, or 3, 2,
I got 45.
Okay, so 45, obviously that last row would dominate. But if this last row that I didn't remember, so I just said 7, 8, 9. If this last row was actually 3 plus 2 plus 2, which is 7, then my second row would be the largest one, and that's 4 plus 5 plus 6 is 15, right? So the norm 1 of A, it's relatively easy to compute, is 15. Okay? If I gave you the inverse of this matrix, it's actually this. And we can also compute one norm of that. And it turns out that this condition number that tells me how well the system behaves when I'm solving AX is equal to B is norm of the matrix itself and its inverse. So basically my condition in the case of this, if I was doing L2 norm or Frobenius norm would be this. In L1 norm would be something similar. in L infinity norm, I can compute that. Either way, I would get a relatively reasonable number of 60. There's no strict cutoff. When is this number like, oh, it's really bad? Like precisely at 1,000. Right? It's not the precise thing, but once you start getting numbers like 10 to the 6, 10 to the 7, those are really ill-conditioned matrices. Okay. So, and why is this theoretically important? Basically, if I ever so slightly change my matrix A, which is this delta A, I just change the coefficients slightly, and I take a norm of that. This condition number is sort of a coefficient that limits how the difference in the solution will change respect to the original solution. So if I slightly changed A, and my condition number is large, this is still going to be large, so there's a chance for the pretty large change in the solution, even though I have changed coefficients of the matrix just a little. And that's the stability problem. And this is just a depiction of one of the problems. I think actually you're getting this. Am I correct that this is actually a picture from the homework that is going to be assigned today? Something similar. Oh, you changed it. Never mind then. Okay. But something similar you will be solving for your homework, and it's slightly similar to that problem of reaction tanks that we solved in class last week. So anyway, the idea is that slight change in matrix A really implies slight change, say, in the radii of these pipes. Okay? And I physically don't want that to influence my solution well, because it's not a well-designed system then. Sometimes these slight changes, if I'm an engineer, okay, slight change will be there by deposition of stuff. Texas has hard water, doesn't it? Okay? There will be scale. You're petroleum engineers. In well bores and so forth, there will be scale, which is not the same as from the water. It's asphalt teams and whatnot that can deposit. Okay? And pretty quickly. So slight change in the radii of the pipe will happen simply by the use of those pipes and by natural processes that happen, right? So I don't want to design a system that I design systems for steady state flow that behaves well one moment and then there's slight deposition on the pipes and I change radii by a few millimeters and suddenly, boom, I have instability in the flow for the system, right? That's a poorly designed system. So I want to avoid ill-conditioned matrices, okay? And as an engineer, I would basically go and see what the steady state flow looks like and how does solution behave through it. Excellent. So let's see just like one example. Let's open up Python. And this actually 1, 2, 3, 4, 5, 6, 7, 8, 9 that I come up with when I don't know what to come up with. It's actually an ill-conditioned matrix, so it's actually a bad idea to come up with it. But let's actually test it. Let's type it in and see. And here's 1b. So I'm going to solve this AX is equal to B using this matrix. And then I'm going to just slightly change it to 9.1. Okay? And solve CX is equal to B. And see how far off are those solutions. Technically, I don't expect those solutions to be very far because the matrices are not very far. Let's see. So I'm going to call this Lecture 6, Spring 2019, condition number. So my A, import numpy is NP. My A is NP array. 1, 2, 3, 4, 5, 6, and 7, 8, 9. And my B is NP array. 108 and 10. So I'm just gonna say, I'm just gonna use the solver. Did I type everything correctly? Okay, and print X. So get this solution that has e to the plus 17. That's the first sign of trouble. Now let me just vary this slightly. And just put this 9.1 here. And I'm going to call this C. And I'm going to call the solution to this one Y. And I'm going to print it. Okay. So vary coefficients of matrix slightly. And its really variation is just in this 9.1. 0.1 relative to all the others, 1, 2, 3, that's a 10% change of 1, and almost, it's 1% change of 9, essentially, give or take, right? This is not a large change of one coefficient. Let's see how my solution Y changes. It's still there, but let's look at this. This solver is actually pretty much optimized. Probably my Gaussian elimination wouldn't be as well. Oh, I was like, wait a second, I don't see much change. I'm like, good job. Yeah. I'm like, good job, Python. That's the thing, when you're using some other solvers, you don't know how well they handle. There's something called preconditioning that they can go and do when they identify a matrix that is misbehaved. And I don't know whether they're doing it. So I was like, oh, something changed. So do we see the change? Suddenly, this actually looks like a reasonable solution, right? This one is definitely not physical. So this is a sign of a matrix that is ill-conditioned. If I actually went and computed the condition number, so I can just compute it by hand. I can do np, it's linalg.norm of A times np linalg norm of A. Oh, and maybe printing it would be a good idea. I'm going to get a relatively large number. So even something like 285 can, inverse of A. I think it's linalg inverse. We're going to test it. Yes. So these are all built-in functions. I'm just for simplicity using all of the built-in functions that you should know about. We've been busy figuring out how to solve things ourselves.
Are we supposed to get the same
Very similar, yes. How different is your solution?
just by one?
By one, that's not a big deal. Again, when it's unstable, just different by one. That's the sign of instability, actually. Because your computer will have a slightly different numerical accuracy than mine, possibly. Yes? So these are the matrices that we should avoid. Sometimes when we cannot, there's an entire area. You can get a PhD in applied mathematics just working on preconditioning and making unstable matrices like this, which are rather typical, for instance, in reservoir simulation, making them more stable and making algorithms more accurate and faster. Okay? Excellent. Okay. So another one is actually, it has a famous name because it shows up often. And that is so-called van der Waals matrix. What we can see in this one is that I have sort of orders of magnitude of change in coefficients, and that will do it. So I go from 1 to x3 to x3 squared, and if x3 is 10, you will see orders of magnitude change in coefficients, and that is commonly causing ill conditioning. And again, the moment it has a name, it shows up often. Here's an example where it actually shows up. If I was trying to find a polynomial, in this case, I'm fitting a fourth order polynomial that is going through precisely 5 points. I have 5 coefficients that I'm looking for in this polynomial. And I would basically take this y's of these points. Those are my f of x's, and these are my x's. Okay? And I can set up a linear system that looks like that van der Waals matrix to actually find this. So my first equation is P1 200 to the fourth plus P2 200 to the cube plus P3 200 to the second order, and P4 times 200 plus P5 equals to 0.746. That's my first equation. And it's a linear equation in P1, P2, P3, P4, and so forth. And that's how I set up all the others, and that gives me a linear system. So finding polynomials like this using linear systems is actually a bad idea because those systems are not well behaved. And we will move on to doing it differently in our curve fitting. Okay? You could do this exercise. I'm going to skip it for now, but you can do this exercise on your own, just like trying to fit a 2 polynomial, and it's still going to show up as a problem. Okay? So this essentially concludes our treatment of linear equations. Not completely, because we're going to the curve fitting, and curve fitting is going to end up an exercise in solving linear systems. But it's a very important exercise that we do often when we're analyzing data. These days, everybody is calling machine learning is the buzzword. Machine learning is curve fitting on steroids, okay? So it's really not much more than curve fitting. So let's get going into that. I will post this lecture so you don't have these slides, but I will post them right after class. So let's dive in right away to curve fitting. So we are progressing steadily. We're going to spend about three class lectures on curve fitting. I will not have time for interpolation, and then we will jump into ordinary differential equations, also about 3 lectures. And at the end, I will probably have a lecture for like introduction to numerical integration. Okay. So we will fit that in. So essentially, we will complete our semester in about 2.5 weeks. Is everybody ready for that? Maybe.
Do you have the date for the finals yet?
Yes, they're posted. Final is on May 16 morning, right?
I think so, 9 to
Yeah,
12.
9 to 12, something like that. But I will put together final that is not going to be much longer than what you had in exam 1 and exam 2. Since we had exams, 2 exams, it's plenty of exam time. I'm not in favor of these 3-hour long things. I do that only to graduate students. So, they have to be trained for longer races, okay? But again, we've had plenty of testing, so it's probably going to be like a 2-hour exam. And not much, maybe 6 problems instead of 5, something like that, okay? So normally we've seen these 5 problems on exams, and we're just going to do 6, okay? Any other? Yes, now that we're addressing, we may as well talk about it. So this is what I standardly do. So we're now going to go through curve fitting and ordinary differential equations and numerical integration 1 lecture. So all those lectures will get 1 problem. So that's 3 problems. And the other 2 or 3, depending how I compose exam, will be sort of review of the previous stuff. That's essentially how it's going to go. Yeah?
Only 1 problem for curve fitting, differential equations, and numerical methods?
1 each.
1 each.
So that's like 3 problems right there. So half of it will be newer material, right? And the other half will be reviewing stuff from before. Exam 1, again, was just like really up to the programming. So all of these problems will test, or most of the problems will test programming in that form. I'm not going to necessarily specifically ask you. Maybe there will be some short questions here and there, but to solve all of these, you got to know a for loop, right? Or while loop, or yes?
So can I bring the cheat sheets from the
Yes, so you put together, you kind of keep collecting your cheat sheets. And basically for the rest of the material, you'll be allowed to have 1 more. So bring all of them. Or copy somebody's good cheat sheet. I know somebody in first row who has very nice neat handwriting. Contact her after class. So, anyway, yeah? All right. Any other questions about the final? So again, it's cumulative, so your cheat sheets, they're cumulative. And by now, I hope you know where everything is in those cheat sheets when you're referring to them, right? That's the whole point. Okay. So curve fitting is essentially a process of finding simple analytical function that goes through the data. Okay? So I can have, let's say that the data is given by this example here. It's a little wicked zigzagging example. So it's actually a question of how would I would like a function. I would just like a function because function is easy to program. And then I'm going to use that function as a prediction in some similar case. That's why I want the function. Okay? Let's say that I know how markets have behaved in oil prices in the past year. And if I want to extrapolate that, that's a bad idea, it never really works, but if you want to just extrapolate plainly based on the past behavior, you want just a function that will give you over the course of the year what those prices will be, or maybe as a function of something else that those prices depend on. For instance, cumulative production in Permian or the world or both. So the functions could be as complex as we'd like them to be. However, in the simplest case, we typically just have, well, y is an f of x, okay? I have a simple function of 1 variable. So if I have data that is going like this, I have 2 options. One would be going directly through the data and trying to hit all of these data points. That's called interpolation. We're going to skip doing interpolation. It's important to do it in cases where I know that these points that I need to hit are precise. There's exactly what they are trying to be. Then I do want to interpolate, and I can always find a polynomial of degree that is high enough that will do this. Most of the data, however, is not as precise. And technically, it might have a built-in error. Okay? Especially if I'm plotting it against only one variable, but I know that technically it depends on 3 variables that I'm not necessarily plotting. Then trying to fit it precisely is actually overfitting, it's dumb. Okay? And then I'm just going to try to find the trend. Okay? And that trend should be in some way, and we're going to define close, it should be as close as possible to all of the points. Not even necessarily hitting all of them. So this is sort of a trend, general trend of all of these, average trend, if you will, of all of these points. And in this particular case, doesn't hit any of the points precisely. So this is some general imaginary data. Now let me give you some petroleum engineering examples. First one is capillary pressure saturation. Do those two terms mean anything? If they don't, in petrophysics, will suddenly start meaning a lot. When do you have petrophysics next year?
Next semester.
All right, so basically what you do, you get a core. You first flush it, let's say the sandstone with water, and that's the so-called wetting fluid that saturates the core completely. It's wetting because quartz surfaces are preferentially wetted by water. Water likes quartz surfaces. Water likes glass. Your glass, if you were driving here or if you were coming by bus, that glass kind of spreads. The water spreads on the glass, unless glass has some sort of protective film, and you can do that on your car too, that makes water kind of bubble up and just roll down. Okay? Your rain jackets are the same, so kind of oily protection layer on a rain jacket will make the raindrop beat up and roll down, and you will stay dry. Okay?
Just like an umbrella.
Just like an umbrella. Unlike your cotton shirt that loves water, right? So whether you sweat or it's raining on you, you're soaked. Okay? So those are wetting properties of fluids. And when we have two fluids, they're typically defined with some two fluids. We don't think of air as being there, but air is fluid. So compared to air, water is wetting in all of these surfaces that I mentioned before. We often have either air or gas, oil, and water in subsurface. And I first basically saturate with wetting fluid, and then I'm trying to push in non-wetting fluid, the one that doesn't preferentially wet the surface, and that takes some pressure. The difference in the pressure between those two fluids is called capillary pressure because their chemical composition is different, molecules are different. There is a surface that forms between the two fluids. They're immiscible. Water and oil hydrocarbons are immiscible. And that surface can withstand certain pressure difference, and it curves in response to it. The smaller the pathways that I go through, the larger this curvature is. Right? This kind of, I bend more over shorter distance. And that makes it harder to push fluids in. Okay? So we measure properties of that type of displacement with a curve like this. So essentially, I start with saturation of water 1. I start pushing in oil or maybe gas, and I push in and try to displace water, and then I go in a curve like this. At some point, so I have certain distribution of these cross sections in my rock where fluids are going through. It's sort of at some point I hit a critical value where I can kind of get through most of those tiny pore spaces because I have enough capillary pressure. Okay? Because it's related to the radius of these pathways, and at that point I can kind of mostly displace the wetting fluid that I have in there. There's always some, this is actually a normalized curve, there's typically some residual in the corners that I cannot get out. And then I can start decreasing the pressure, so this was drainage. Then I start decreasing the pressure, and I will go back. This being wicked porous media, there will always be some residual of oil in there when I go back. Our production is typically a sequence of these drainage and inhibitions. Okay? when we first spoke in, that's called primary drainage, like basically things are just, I'm draining the oil based on the pressure that exists in the reservoir. After that, I might come in with a water flood. Okay. That's in this case, an inhibition process, if I'm doing that in a sandstone, and try to push oil. And we need to understand how these things happen, so we often do a lot of lab experiments like this that mimic the process, so we understand how a reservoir behaves. Great. So having these measurements, which I do in the lab, I'm trying to fit a model to it so I can just describe it as a function. And one Genuchten model is given here as an example. This long story was just to motivate why are we doing this curve, right? But you will learn much more in petrophysics about it. So that's where I have nice data because I'm doing one experiment, okay? And I'm measuring saturation by weighing the core, right? It's a simple weight, the mass balance. And I have the pressure taps at the beginning, in the front of the core. The difference in the pressure reservoirs for oil and water will give me the capillary pressure. Great. However, sometimes I'm going to pull out the core from a reservoir. And I'm going to pull out multiple cores. Those multiple cores will have different porosities. And possible multiple reservoirs as well. Depending on the degree of sedimentations, have you done sedimentary rocks yet? Well, you're doing it now, you're about to do it. Again, you will figure out the sedimentary rocks that if you press sand grains together and then you let go over time, the water will deposit the cements or whatever fluids are passing by will deposit cements that are binding those particles together. And then they get buried deeper and deeper. It's actually happening together. And during the burial, the water will go out. And the sandstone itself, this cementation will limit the space. And as you have more cementation, you have less pore space in between the particles, so you will reduce the porosity typically as you go deeper. Okay. So depending where your reservoir is and how many times it went to this up and down burial and up and down motion over the geologic time, it has experienced different degrees of cementation. So that results in the porosity that we see today. So typically when I have a core, I measure the porosity by filling it with helium, and I have that measurement here. And I can also run water through it or whatever other fluid and measure permeability to that fluid as well. And then I want the relationship between the two. I'm well aware, and you will be even better aware after you go through petrophysics, that permeability is not just a function of porosity. It's a function of porosity as well as those grain sizes that are composing the rock. Those are the two minimum things that define porosity. Of course, the degree of cementation and so forth is important as well. And the more complicated the rock, the less obvious that relationship is. So often we do a lot of measurements and are trying to get what that relationship is. Simplest one would be just permeability versus porosity. So here's a whole bunch of sandstones. These are all clean. Fontainebleau is a very clean sandstone. It has only quartz and quartz cements. Nothing more to muddy my water. So basically these are the measurements as clean as they get, but look at the number of overlaps. Okay? I can't interpolate this and find the function that goes through all the points. That would be really dumb. So I'm looking for a sort of a general trend, and that's what curve fitting is. Linear trend doesn't look good here. Okay? So just doing a straight line through this ain't gonna cut it. Or it will, it's just gonna be a very poor fit. So there is a curved line that is maybe more parabolic or even exponential that fits through this much better. So I have in this basically outlined what you need to do. You need to look at your data. You can blindly fit something, and linear fit, just a straight line for something, is always the simplest and gives you some sort of a trend, but it's not necessarily a good idea to do. In neither of these cases, linear would do awfully here. I'd be far from everything. And in this case as well, so you need to look at the data and kind of gauge what type of function would fit well. That function has certain parameters. If I was a linear fit, I have two parameters, right? Describing a linear function. And the whole exercise of curve fitting is finding the function or those two parameters that fit my data well. Okay? That's about it. Linear systems play a huge role in it. And the only other thing that we need to decide is how do I define fit well? Okay, I need to be more mathematical for computer. Computers are dumb, as we know. They don't draw things through a bunch of points. I gotta tell them precisely what to do. Okay? So we're gonna get to this next time, but essentially, you're gonna measure for all these points, you're gonna assume a trend through, and then we're gonna see how far away we are from these. We're gonna take a square of these distances and sum them up. And that's called least squares. So this is my model yi, and this is my actual data. I'm gonna take square of that, sum it up, and I'm gonna try to find the minimum of this, or parameters of the model that minimize this. And that's gonna give me linear systems that I'm gonna solve. Okay? All right.